manifold diffeomorphisms given by Dehn twists along ciphered fibered spaces. So this is an interesting class of diffeomorphisms. They have some close connection to algebraic geometry. They're also a large source of potential candidates of non-trivial elements in the mapping class group. Yeah, specifically I'll focus on Dehn twists on 4 manifolds that admit symplectic structures. Yeah, and this is all going to be joint work with Hokuto Kono, Jianfang Lin, and Anubhav Mukherjee. Okay, so let me get started by explaining what Dehn twist on a ciphered fibered manifold means. Yeah, so I'm going to start by explaining what's the sort of local model for this diffeomorphism. So here we start out of a ciphered fibered free manifold that I'll call Y. And in the local model, this is embedded in the product of an interval cross Y. And it's embedded at slice 1/2. Okay, and we're going to define certain diffeomorphism of this interval cross Y, and that's going to be the Dehn twist. So this is going to be a diffeomorphism of interval cross Y. It's going to have the property that it fixes the boundary. Moreover, it fixes a small neighborhood of the boundary. And it's well defined up to isotopies. Okay, so this is going to be the ciphered fibered Dehn twist. And what's the construction of this Dehn twist? Well, a ciphered manifold is a free manifold that has an action of the circle, which is fixed point free. So we're going to use this action to produce this Dehn twist. And the way we do this is, well, let's call T the coordinate in the interval, then maybe Y a point on the free manifold, then the Dehn twist sends T comma Y to T comma e to the 2 pi I T times Y, where this denotes the ciphered circle action. Okay, so this is the ciphered S1 action. Okay, so this is the model case for the ciphered fibered Dehn twist. So how can you think about this? So you may want to think of ciphered fibered space as a family of circles over an orbifold surface. It's some family of circles where there's some singular fibers where the nearby ones collapse to multiple covers. So if you think of Y as a family of circles, you might think of interval cross Y as a family of annuli. And then what you see on each of those annuli is the classical Dehn twist. Okay? So fiber-wise, you just see the classical Dehn twist of an annulus. Okay. And well, I mean, this is not quite true on the singular fibers. You'll see some iterates of the classical Dehn twist. Okay. Any questions about this? Okay, and yeah, so we're gonna be interested in this sort of diffeomorphism. So whenever you have a 4 manifold with a ciphered fibered 3 manifold embedded in it, then you can implant the Dehn twist. And we're gonna be looking at a special case where the Dehn twist is performed along the boundary of a four-manifold. Yeah, so here we're going to have M. This is a compact four-manifold whose boundary is ciphered fibered space. And then you can look for a parallel copy of the boundary and implant the ciphered fiber Dehn twist along that parallel copy, and that's what I'll call the boundary Dehn twist. So this is mapping class in the diffeomorphism group of M relative to the boundary. Okay. So in this case where the manifold has the boundary, there's a simple description of when this element in the mapping class group is smoothly isotopic to the identity. Namely, one can see, it's not very difficult, that the boundary Dehn twist is smoothly isotopic to the identity, rel boundary, if and only if the circle action from the ciphered fiber structure, this extends over to the four-manifold bounding Y, not quite as a circle action, but just as a loop of diffeomorphisms. Okay, so this extends to M4 as a loop of diffeomorphisms. Okay. Okay, so I'm going to be studying, I'm going to be talking about boundary Dehn twists on four manifolds, and I'll be interested in the case where M is a symplectic manifold with contact boundary. Okay. So yeah, this Dehn twist diffeomorphisms, they have some close connection to singularity theory, which I want to briefly explain. So yeah, let me discuss the following example, which is the main one that I have in mind, and that comes from studying the Milnor fibration. Of surface singularities. So here I'm going to look at x, comma 0. This is going to be the vanishing locus of some polynomial f in three complex variables. And this is going to be a polynomial that has an isolated critical point at 0. Okay, so I'll call this is going to be an isolated hypersurface singularity. I'll abbreviate it to IHS, whose complex dimension is equal to 2. And I mean, technically, I only care about the germ of the singularity at the singular point. Okay, so one way of studying hypersurface singularities using topological methods is by analyzing the Milnor fibration of such a singularity. So what's the Milnor fibration? So the equation f equals 0, this describes some hypersurface in a fine space C3 with an isolated singular point. And this is the fiber over 0 of our map f. But then you can consider a nearby fiber. Let's call it f equals t, where t is non-zero and small, and then this will be non-singular. So we want to consider all this family of smoothings of the central fiber all together, and this is what's the Milnor fibration. So more properly, what we do is we consider a ball of small radius epsilon in C3, and then we look at a possibly even smaller ball of radius delta in the complex plane. Okay, and so maybe in formulas, I'm looking at the following fibration. Okay, so we have a family we have a family fibering over the punctured disk of radius delta in the complex plane. And the total space is the preimage under F of that intersected with the ball of radius epsilon. And well, classical result by Milnor is that if you take the epsilon extremely small and the delta possibly even smaller, this is a fibration of compact manifolds with boundary. Okay, so this is a smooth fiber bundle of compact, in this case, 4 manifolds with boundary. Okay, I will call the fibers of this family by M. Okay, and this is provided provided epsilon is chosen sufficiently small and delta is also chosen sufficiently small compared to epsilon. And so if you have if you have singularity, then you can look at its Milnor fibration, and well, this is a fiber bundle over a punctured disk, so you can look at the monodromy along the boundary, and this will define diffeomorphism. That's the monodromy of the Milnor fibration. We're going to denote it by the letter psi. And this is going to be diffeomorphism of M. M is the Milnor fiber. And this is, so one can see that, in fact, there's a sort of canonical trivialization of the boundary fibration. And that this respects that boundary trivialization. It's a diffeomorphism that's going to be acting trivially on a neighborhood of the boundary. Okay. So the monodromy of singularities is a classical topic of study, but really what's more classical is the study of the monodromy acting on the homology, the singular homology of the Milnor fiber. And there's lots of things known there, perhaps most notably the monodromy acting on the homology of the Milnor fiber acts quasi-unipotently. So the eigenvalues, the complex eigenvalues of the monodromy are roots of unity. But from the point of view of just the smooth mapping class group, not much has been done. So I'm going to be looking at a special class of hypersurface singularities. These are called weighted homogeneous isolated hypersurface singularities. So to give an example, you could look at something like this equation. And the singularity defined by this equation, this is the cone over an elliptic curve in P2. More generally, you can look at exponents A, B, C. And this is the so-called Briscorn singularity. Okay. So here the weighted homogeneous refers to the fact that there's a C-star action on the affine space C3 whose weights are positive and which makes this equation homogeneous with respect to that C-star action. Okay? This is a special case that's quite interesting because it turns out it's not difficult to see that the boundary of the Milnor fiber, so this is going to be a 3-manifold, and this is a ciphered fibered 3-manifold. And moreover, the monodromy is closely related to the boundary Dehn twist on the Milnor fiber. So, and the monodromy of the Milnor fibration has the property that if you raise it to a suitable power d, then it agrees with the boundary Dehn twist on the Milnor fiber. Okay, so for a suitable positive power, the monodromy of the Milnor fibration of a weighted homogeneous singularity matches up with the boundary Dehn twist. Okay.
What is this number in terms of ABC?
Yeah. So in this case, D would be the lowest common multiple of A, B, and C, for example. Yeah. You can compute it from the D. You can determine from the weights of the C-star action. Yeah. Okay. Any other questions? I couldn't quite hear. So in the particular case of weighted homogeneous singularities, in fact, Milnor proved that the homological action of monodromy is diagonalizable over the complex numbers and has eigenvalues, roots of unity. So in particular, there's some, if you take some power of that, it acts trivially on the homology that matches, that checks up with the fact that, well, if you raise the monodromy to some power, you get the boundary Dehn twist. Yeah. Okay, thanks for the question. So singularities of surfaces, they, at least in the weighted homogeneous case, by studying their monodromy, that naturally leads to studying these boundary Dehn twists along 4 manifolds with ciphered fibered boundary. Okay. So let me discuss now the main result. More general than Milnor fibers, one might consider some arbitrary symplectic filling of a ciphered fiber space with a suitable contact structure. Let's look at Dehn twists on more general symplectic fillings. So here's the main result that I'll discuss today. So let Y be ciphered fibered 3-manifold, which is furthermore going to be a rational homology sphere. And for the purposes of this theorem, it's quite crucial what's the orientation of the ciphered fibered space. So I want to orient it as the boundary. So every ciphered fibered space is going to be the link or boundary of a singularity. And I want to equip it with such orientation. So there's many ways of phrasing this. I'll just call this orientation the negative orientation. Different way of phrasing this is that we're orienting Y so as a principal circle bundle over an orbifold surface. It's going to have a negative orbifold degree. But yeah, you can just think of it as the orientation that you get on the ciphered fibered space when it's oriented as the boundary of a surface singularity. And when you equip the ciphered manifold with this orientation, then there's a canonical contact structure on the ciphered fibered space compatible with the orientation and transversal to the circle fibers. So I'm going to be looking at this canonical contact structure. Okay, and then I consider N4. This is going to be a compact, symplectic filling of Y3 equipped with the canonical contact structure. So namely, there's a symplectic form on this 4-manifold, which near the boundary is modeled on the symplectization of this contact structure. And the crucial property on this symplectic filling is that it's going to have a positive B+. Okay, so if you look at the intersection pairing on the H2 of this compact 4-manifold, the dimension of the positive eigenspace must be non-zero. So then the theorem is that the boundary Dehn twist on this 4-manifold has infinite order in the smooth mapping class group. Okay, so in particular, it's non-trivial, and furthermore, it has infinite order. Okay. Yeah, so so there's this very general situation where if you want to study the boundary Dehn twist, as long as you have symplectic structure and the filling is positive B+, then the boundary Dehn twist will always be non-trivial to infinite order. And maybe let's compare this result with what happens in other categories. You could, for instance, look at the topological category. And here there's results by Orson and Powell which under mild assumptions tell you that diffeomorphism that acts trivially on the homology will be topologically isotopic to the identity. So for instance, in this situation, if you furthermore assume that the 4-manifold M is simply connected, then you can conclude that the boundary Dehn twist is topologically isotopic to the identity. Okay, so it's trivial in the topological mapping class group. And the reason is that the boundary Dehn twist acts trivially on the homology of M. And yeah, Orson-Powell proved that a 4-manifold that's simply connected and has rational homology sphere boundary, and there's a diffeomorphism acting trivially on the homology, then that diffeomorphism is topologically isotopic to the identity. Okay. Okay, so this gives examples of exotic diffeomorphisms, and maybe a few more comments. So the assumptions on the theorem are quite crucial. So for instance, if B plus of M is taken to be 0, then the conclusion breaks down. For instance, you could look at so another source of symplectic fillings of ciphered fiber 3-manifolds that are not Milnor fibers is taking instead the minimal resolution of the singularity, or that's the canonical negative definite plumbing of a ciphered, negative definite filling of a ciphered fibered 3-manifold. So if you look at this particular case of the minimal resolution, of an isolated hypersurface singularity, then you will see that the boundary Dehn twist becomes smoothly isotopic to the identity. That's because the circle action from the ciphered fiber 3-manifold will extend to the minimal resolution. Okay. I'm going to erase this board. Yeah, so a particular consequence of the theorem, going back to the singularities, is the following corollary. So if x0 is an isolated hypersurface singularity, which is weighted homogeneous, and of the correct dimension, which for us is complex dimension 2, then we get the following application, which is that if the singularity is not analytically the same as one of the ADE hypersurface singularities, then the monodromy of the Milnor fibration has infinite order. Is it equivalent ADEN? Oh, thank you. So if X is not, thank you, is not isomorphic to an ADE singularity, then the monodromy of the Milnor fibration has infinite order in the mapping class group. Okay, so the ADE singularities, these are special class. You can think of them as the quotient of C2 by a finite subgroup of SL to C. This turned out to be described by a single equation in C3. We obtained this conclusion, and that's because you can characterize the ADE singularities as those for which the Milnor fiber is negative definite. Okay, so equivalently, hypersurface singularity is, yeah, maybe let me write it on the side. So ADE singularities are those for which the Milnor fibers is negative definite. Okay, so for a singularity that's not AD, the Milnor fiber will have, at least when the boundary is a rational homology sphere, will have positive B plus. Hence, by the theorem, since the boundary then twist is infinite order, so is the monodromy, which has the property that if you iterate it, agrees with the boundary Dehn twist. Yeah, so the converse of this statement is a classical theorem. It goes back to Turina and Briscorn. So they proved essentially the converse. So said differently, if you have an ADE singularity, then the monodromy of the Milnor fibration has finite order in the smooth mapping class group. So this follows by an explicit construction that is known as the simultaneous resolution. The simultaneous resolution of the ADE surface singularities. Okay. Yeah, maybe I should say that this sort of behavior is quite special to singularities of complex dimension 2. So if you look at isolated hypersurface singularities of weighted homogeneous type in higher dimensions, then the monodromy of the Milnor fibration will have a finite order in the smooth mapping class group under mild assumptions. Like, for instance, whenever the link of the singularity is an integral homology sphere, then it will have a finite order monodromy. So this is a behavior that's quite special to the surface case. Okay, so maybe I'll pause for questions if there's any. Yeah. So in this theorem, yeah, that's a good question. Probably I don't have a counterexample. I would imagine you can drop it, but yeah, our techniques only deal with rational homology spheres. So in this conclusion, there's no assumption on the link of the singularity being a rational homology sphere, and that's because when it's not a rational homology sphere, you can prove this by a more elementary homological argument. But to get this statement, we definitely use the fact that it's a rational homology sphere, but yeah, possibly you can drop it. I don't know. That's an interesting question. Okay, so now I'm going to move on to discussing a little bit some of the tools that go into studying these diffeomorphisms using gauge theory. So I'm going to focus on special class of tools coming from family Seiberg-Witten invariants. And yeah, I'm going to be quite impressionistic in the description of these tools. I won't go into much detail, but like roughly speaking, if you have a four manifold, if this has no boundary, then you may assign to it numerical invariant. That's the Seiberg-Witten invariant of M. I mean, you need to choose a spin C structure and such things. I'm just going to put all those things under the rug. And you might also want the B plus of your manifold to be positive. Even if it's positive, if it's 1, then you run into potential wall-crossing issues, and this is really a chambered invariant, and you might have to make some additional choices to make it well-defined. But that's roughly the picture. And in the case when the boundary of the free manifold is non-empty, and it's some free manifold Y, then the analogous construction assigns not a numerical invariant, but an invariant that lives in the Floer homology of the boundary. And I'll use the Heegaard-Floer terminology, but really I'm looking at the monopole Floer homology groups defined and studied by Kronheimer and Mrówka. Okay. Yeah. So whenever you have a manifold with boundary on a free manifold, there's a relative invariant of that living in the boundary. This is obtained by counting irreducible solutions to the Seiberg-Witten equations, if that means something to you. And this theory works well when you start adding parameters. So you could more generally look at diffeomorphism of this 4 manifold with a boundary. Under suitable conditions that I won't really explain, you can associate to this diffeomorphism a corresponding invariant that I'll denote FSW, family Seiberg-Witten invariant of this 4 manifold equipped with diffeomorphism. And this is going to be a class in the monopole Floer homology of the 3 manifold. If this lives in a particular grading, then this will live in that grading plus 1. And the idea is that, well, you can think of a diffeomorphism as giving you a family of 4 manifolds over a circle just by taking the mapping torus construction. Okay, so that diffeomorphism associates a family of 4 manifolds over the circle, and then you carry out, then you study the Seiberg-Witten equations simultaneously on all fibers of this family, and you count how many solutions there are. And that's what produces this type of invariant. So it's just the parameterized analog of the ordinary Seiberg-Witten invariant. And yeah, so we're going to use these tools to study these Dehn twist diffeomorphisms. Yeah, so an important property about this family Seiberg-Witten invariants is that they satisfy nice gluing formulas that you can use for performing calculations. So there's the following formula. There's many variants of this. I'll just discuss some special cases. These have all been studied by Jan van Lien. Yeah, let me not do the general case, but rather let's consider the situation we're interested in, where we have 4 manifold with boundary on ciphered fiber 3 manifold, and we're looking at the boundary Dehn twist on that 4 manifold. Yeah, so here you can sort of separate this 4 manifold into 2 pieces. You can separate it into a piece that's just another copy of M, and another piece which is copy of interval cross Y. And the diffeomorphism we're interested in, the Dehn twist, is supported in this interval cross Y region. So whenever you have this sort of situation, you can compute the family Seiberg-Witten invariants on M by suitable contributions coming from the two pieces. So in this case, the gluing formula looks something like this. So the family Seiberg-Witten invariant for the boundary Dehn twist on M, you can compute as follows. Okay, so there's going to be, so this interval cross Y is a cobordism from the three-manifold Y to itself. But you can also, so there's a cobordism map on the monopole Floer homology. It's just the identity. But you can also consider a version of this cobordism map that equips the cobordism with a diffeomorphism. And that gives you a cobordism map between the Floer homology of Y to the Floer homology of Y. And you just evaluate that cobordism map on the ordinary Seiberg-Witten invariant of M. Okay, so this is sort of a cobordism map associated to the Dehn twist acting on the local model interval cross Y. Okay, so it's the effect of the Dehn twist on the monopole Floer homology. Okay, so using this gluing formula, then, well, you can try to compute both pieces and use that to show that the family Seiberg-Witten invariant is not zero. So let me describe what's the calculation we did. So the calculation is the following. So M is a compact symplectic filling of a Seifert rational homology sphere. And we're going to put some strong assumption on the monopole Floer homology of the three-manifold, namely that the reduced monopole Floer homology has rank 1. So examples that satisfy this property are, for instance, the Brieskorn spheres sigma 237 or sigma 2311. So in this case, our computation is the following. So the HF plus monopole Floer homology of this three-manifold, this looks like something like this. Okay, so this is the U tower, and that's the additional summand corresponding to the fact that the reduced Floer homology has rank 1. This is going to be grading given by the D invariant. This is D invariant minus 1, and so on. And our computation is that, well, the family Seiberg-Witten invariant of, that the ordinary Seiberg-Witten invariant of M is going to be a non-trivial element in this first summand. It's going to be a generator of this summand. And then the cobordism map associated to the Dehn twist on the cylinder merely just takes this element to a non-trivial element here. Okay, so this is the cobordism map associated to the Dehn twist. So this is going to be, under these assumptions, it's always going to be a non-zero map. Okay, so from the gluing formula, you get that the family Seiberg-Witten invariant for the boundary Dehn twist on M is non-trivial by the gluing formula. Okay, so the harder part in this story is to compute this cobordism map associated to the Dehn twist. So I won't say too much about that. All I'll say is that the calculation of this cobordism map relies on explicit understanding of the moduli spaces for the Seiberg-Witten equations on Seifert-fibered spaces, and this was studied by Rofka, Oshbath, and you, and we use the techniques that were developed in that paper to do explicit calculations. Yeah, so in the remaining time, let me discuss some further applications. So let me discuss Dehn twists on other four manifolds. So we've been looking at Dehn twists on the boundary of a symplectic filling. Could look at the following alternative paradigm where there's a correspondingly strong result. So you could, instead of looking at symplectic filling, you could look at a cap with B plus equals to 0. So we look at the Seifert-fibered three-manifold Y oriented as the link of a singularity. And we could look at a cap with B plus equals to 0 and consider the boundary Dehn twist on that. And then there's a very general result due to Kang, Park, and Taniguchi. Who proved that in this situation, the boundary Dehn twist is always non-trivial to infinite order. Okay, so this is an alternative situation where the boundary Dehn twist is non-trivial in huge generality. And well, then you could, so another situation that works quite well is if you take a symplectic filling of Y and you close it up with a cap with B plus 0. So you could glue a symplectic filling with a cap with B plus 0. And let me not state the general result here. Let me just give you an example of such a situation. So, for example,
Sorry, could you repeat what was the statement in the first part?
Yeah, so the statement is that if you have a Seifert-fibered space oriented as the link of a singularity, and if you choose, suppose you have a cap of these three manifolds, it's a four-manifold whose boundary is Y with the orientation reversed, and this is negative, and this has B plus equals to 0. That's the singularity case? No, so it's a bit confusing with the orientations. So the minimal resolution has boundary Y, but by cap I mean the boundary is Y with the orientation reversed. Oh. Okay, so for the minimal resolution it doesn't work. You have to orient things carefully. Yes, just choose cap for Y oriented as a link of a singularity. Then under these assumptions the boundary Dehn twist has infinite order. Okay, so you could wonder, well, you take a symplectic filling and you glue in a cap like this, does the Dehn twist remain non-trivial, given that it's non-trivial on both pieces? And yeah, so this is a situation that works quite well. Let me just describe it with an example. So for example, you could look at the Brieskorn-Fehr sigma 237. This is the boundary of a plumbing of this sort. Okay, so the vertices mean there's a disk bundle over the sphere with Euler number, the number shown, and we're looking at the boundary of such a plumbing. And if you add an additional -2 vertex here, then you obtain instead the Briscoe sphere 2, 3, 13. And well, there's a 2-handle cobordism from 237 to 2313, which is going to be negative definite. So we can take, for instance, the Milnor fiber of the Briscoe singularity 237. We could compose with this 2-handle cobordism that takes us from sigma 237 to sigma 2313. And then sigma 2313 has this property that it bounds a contractible, even Maser 4 manifold. So you could look at C, which is a contractible Maser manifold. And the input from gauge theory here is that the family Seiberg-Witten invariant of this closed manifold equipped with the Dehn twist along sigma 2313 is non-trivial. Okay, so this shows that that way you can show that the Dehn twist on sigma 2313 is non-trivial in this closed 4-manifold X. And furthermore, you can do the following trick. So you can consider same picture, but now you connect some by with C. So this would now be C connect some with C orientation reversed, and then you'll get a compact 4-manifold whose boundary is again sigma 2313, and the intersection form of this guy is the same as the intersection form of this guy. So by a Friedman type result, these 2 manifolds, they are homeomorphic as 4 manifolds with boundary. So this is by a Friedman type result due to Boyer and Stong. Then you could close up again by adding the cap C. And well, here you're doubling a Maser manifold, so you get connect sum with the 4 sphere. So this whole piece here in this picture, this is standard R4. But then under this homeomorphism, you can transport this standard R4 all over to this 4-manifold. And you'll get some codimension 0 submanifold of X, which is a topological R4. I'm going to denote it by R tilde, or something like that. And the theorem that you can prove is that in this topological R4, if you look at the Dehn twist on sigma 2313, this is an exotic diffeomorphism of this topological R4. So the Dehn twist on sigma 2313 as a diffeomorphism of this topological R4 with compact support is infinite order. So this follows from the fact that the Seiberg-Witten invariant is non-vanishing. So it tells you that this Dehn twist is non-trivial on the closed 4-manifold X, and therefore it must be non-trivial in this non-compact 4-manifold R embedded in X. But furthermore, this topological R4 is not standard. So this guy is an exotic R4. And the way you can see that is that so the family Seiberg-Witten invariant satisfies versions of this gluing formula that I was explaining. And in particular, you can show that if a diffeomorphism is supported in a standard 4-ball, then the family Seiberg-Witten invariant vanishes. So in this case, the family Seiberg-Witten invariant is non-vanishing. So this Dehn twist on sigma 2313 cannot be supported in a standard 4-ball. So therefore, this topological R4 couldn't be standard. Okay, so so this is one way of maybe tackling exotica of 4 manifolds by diffeomorphism techniques. Okay, so what's the time left? So maybe in the last 3 minutes, I'll end with discussing a situation that I do not quite understand yet, and I'll just pose it to the audience. So we've discussed symplectic fillings and negative definite caps, gluing those two things, but the really interesting thing would be to take a symplectic filling and glue in a symplectic cap. So gluing symplectic filling with symplectic cap. So this is a situation that doesn't work quite well. There's sort of many natural compactifications, for instance, of Milnor fibers into complex surfaces for which the boundary Dehn twist becomes smoothly isotopic to the identity once you compactify. So for instance, could look at the famous embedding of the Milnor fiber of the Briscoe singularity 2311 inside of the K3 surface. The complement of this embedding is the Gompf nucleus N2. So this is a neighborhood of a rational curve of self-intersection 0 that intersects transversely -2 rational curves. So you're looking at a neighborhood of those curves. And a fact that we proved is that if you do the Dehn twist on sigma 2311 embedded in the K3 surface by this construction, then it becomes smoothly isotopic to the identity in the mapping class group of the K3 surface. So this is quite unfortunate, but you may wonder what happens if you modify the complement of the Milnor fiber by some surgery. For instance, you could do log transform fiber sums. Does that make the Dehn twist survive after you do that type of surgery? So question, modify the K3 surface to obtain a new manifold X prime by doing something like log transforms, fiber sums. Does the Dehn twist remain non-trivial after you do such operations? Does the Dehn twist become non-trivial in the mapping class group of the new 4-manifold? I don't know, and it would be great if someone figures this out. And I think my time is up, so I'll leave it there, and thanks for listening.
Your main theorem, you take the canonical complex structure from the singularities. Did you think about what happens if you take another complex structure?
Yes, so the theorem is a bit more general than what I stated. It works whenever you have, if you have a contact structure that's invariant under the circle action, that works. Under some assumptions, you can take any contact structure that's just homotopic as a plane field to the canonical one. For that, you need some extra assumptions on the Floer homology of the boundary. For instance, when the reduced Floer homology has rank 1, then we can assume that the contact structure is just homotopic to the canonical one as a plane field, not as a contact structure. But beyond that, I don't quite know. I suspect one should be able to make that much more general than what we achieved there. Yeah, just you have a ciphered fiber 3 manifold, which is a rational homology sphere, maybe integral homology sphere. I guess Kang is here. Could ask him. Rational homology sphere, or integral homology sphere, perhaps. And then you have a cap for that with B plus 0. Not symplectic, just cap. Yeah.
But that could be formal on S3.
With B plus, okay. Except for S3. Yeah, thanks. Question? Right. So in fact, without that assumption, we need to use a completely different strategy. This approach, in fact, breaks down. You can show, in fact, that when the 3 manifold boundary, the reduced Heger-Floer homology, when the reduced monopole Floer homology has rank greater than 1, then the family Seiberg-Witten invariant for the Dehn twist on a Milnor fiber vanishes always. So in fact, we use a different strategy. We look instead at equivariant version of monopole Floer homology, equivariant with respect to Z mod P action. The Z mod P comes from the ciphered fiber circle action. And then we have a different argument involving an obstruction coming from an equivariant version of the contact invariant in that setting. So yeah, we have a separate strategy for dealing with the general case. And the advantage of this family Seiberg-Witten approach is that it leads to other applications that are quite interesting. So if you can show the family Seiberg-Witten invariant is non-trivial, then there's additional topological applications you get that you don't get from the other technique. That's why I focused on this one. Yeah, thanks.
That's slightly silly remark. I mean, you said the Milnor fiber orders are special to complex dimension 2, but it holds in complex dimension 1.
Oh yeah, right. I was ignoring 1. Yeah.